Alright, y'all, so the numbering is going to get wonky because we're using a different book, because we're using volume 2 now. So this is volume 2, section 3.1, but in, college boards things, it's something else, but it's okay. So, we're going to look at the product rule, and then we're going to talk about how do you figure out with integration by parts which part is u, and that's going to make more sense after we do the product rule, and then we'll do some examples, and hopefully it goes okay. So, let's take the derivative with respect to x of y equals u times v. Do you see any x's in here? No. So, when we take our derivative, oh, that's an ugly color. That's not ugly, it's just not the lovely ocean dx of both sides. Alright, so what do we do here? We need to use the product rules. So we have dy dx on the left side equals what? Well, what's the derivative of the first? So du dx times the second plus the first times the derivative of the second. Okay. Now, what happens if we multiply by our differential dx? Because dx is everywhere. So let's do that. Let's see what happens. And we're going there, dx. Okay, so then we have dy equals, and we're going to flip this order. So we have v du plus u dv. Okay. Now, right, because like this cancels with that and that cancels with that. Okay, so from here, how do we get, let's backtrack and let's integrate. Okay, so then we have dy is y, so that gives us y, but then this is all, it's just a sum of two things, and we know from our properties of definite integrals, or our properties of integration, that we can have this as separate. We can have v du plus integral u dv. Okay, well that's nice. Because what happens if we just subtract a little bit? So, what are we left with? We're left with y equals, and y is uv, right? From here, from our original thing. So y equals uv, and then we have integral of v du plus integral u dv. Well, if we move this part over here, just with subtraction, then we'll be left with integral of u dv equals uv minus integral of v du. And that is going to be oh so very useful, because if we can figure out how to split up our integral into two parts, then we can integrate those parts. We can integrate using our understanding of those two parts and their derivatives, so we can actually integrate things that are a little bit more complicated. Okay, so write this down, and then we'll get to it. So we have integration by parts. If we have u equals f of x and v equals g of x, and those are continuous functions, functions with continuous derivatives, so that means that they're also continuous because differentiability implies continuity, then the integration by parts formula for the integral involves these two functions is integral of u dv equals uv minus the integral of v du. Nice. This is going to need to live in your brain. So just put that in your brain. Don't let it go. Or at least write it down somewhere that you can see it at any time. Alright, so find the integral of x times e to the x dx. So we're going to think to ourselves, okay, so what part of this is u and what part of this is dv? right? Because that was our formula. Our integral of u dv equals uv minus the integral of v du. So which part of this is going to be u and which part of this is going to be dv? We have x, e to the x, and dx. We want to, and we also want what's inside our integrand to be less complicated for this part. This v du, we still need to integrate. So the thing about e to the x is that whenever you take the derivative of it, it stays e to the x, which is insanely frustrating if you're trying to make your integrals more simple. So perhaps we don't want to use e to the x as our u, this part. Perhaps we want x as our u part, and then e to the x dx as our dv. So if we do that, and every time we do integration by parts, it's really helpful to write this down. You have u equals, and you have, and the way that you write this down, it's really up to you. It's not like, I don't know, something that matters, like Punnett squares or something. I don't know if Punnett squares actually matters where you put things, but if you have u, you should make sure you have u, you have v, dv, and du. That you have spaces for all of those. I don't really care where you put them, just know that these are the ones that you start with. Sorry. Neighbor is a really loud car. So we have u and dv. And so we're going to say that x is u, so then the derivative here is going to be dx. And then dv is e to the x dx, so when we go to our original v, then we just integrate that so we have e to the x. And now we're just going to plug in what we have to here, our formula. So we have that equals u, which is x, times v, which is e to the x, minus the integral of v, e to the x, du, which is dx. And that is x, e to the x, minus, and that's just e to the x, plus c. Boom. Done. Alright, so in this one, what should we do? We have x squared times the natural log of x. And so it helps to think, okay, so which one is easier to take the derivative of, which one's easier to take the integral of? So we have x squared and we have natural log of x. And like technically, yes, we do know like what to do with natural log of x, I suppose, is like x ln x, but that sounds like it's worse. So maybe we should take the derivative of ln. So we have u is the natural log of x, so that means the derivative is 1 over x, and then dv is what's left over, this x squared dx, and then v is going to be x cubed over 3. So now, just plug it into our formula, see if that helps. So we have this integral of x squared times the natural log of x dx equals uv, so uv, x cubed over 3 times the natural log of x plus, or minus, sorry, minus the integral of v du. So we got 1 over x times x cubed over 3, oh, I forgot a dx there, dx. And so, well, this is nice because this becomes very algebra, right? Where we just have, I'm copying this down, x cubed over 3, natural log of x minus, and then pew, pew. So we get 1/3, and then we're looking at the integral of 1/3 x squared dx, and so we just have x cubed over 3 plus c. And, well, that's just 1/3 times x cubed over 3. It's just x cubed over 9, so all we're left with is x cubed thirds, natural log of x, minus x cubed 9ths plus c. Boom. Alright. So let's see. What's next? Oh, we got a definite integral. Okay. So this is, Is that parts? Are there parts there? I don't think so, right? I mean, like, kind of, I guess. We have, like, arc sine of x, and then we have the dx. I wonder what would happen. Like, do we know our integral of arc sine? It's not yet. But do we know our derivative of arc sine? I think we do. So what if we say that u is arc sine of x? So that means that du is 1 over root 1 minus x squared dx. And that means that, and I'm running out of space, I'm just going to move this over. We have dv is dx, because that's all that's left over. And then v is x. So, but do we change our variables that we're integrating respect to? No, we did not. So we can keep our bounds the same, because we're not doing like a u substitution. Like, yes, we're using u, but it's not a u substitution. And so our bound can still stay in terms of x. So, we have our integral from 0 to 1 of arc sine of x, and I'm just gonna, wow, that's a really bad x. Arc sine is just so much effort to write, so I'm just not gonna write it right now. So we have uv, so that's x arc sine of x, and that's going from 0 to 1, because fundamental theorem of calculus, right? We still need to evaluate at our bounds, our antiderivative, minus integral from 0 to 1 of v du, that's x over root 1 minus x squared dx. And all I did was multiply this, this 1 times x just to simplify my life. Okay. Well, that's nice, I guess. We have this x arc sine of x part in the front, but this part is a little bit complicated, but it's actually not terrible. So let's take a brief aside and just look at what we have here. So over there, what do we get? We have something that we could use a u substitution for. So we have u equals 1 minus x squared. I guess we shouldn't use u. What's a different variable? W? So we can have w substitution. It's funny. Okay, so dw is negative 2x dx, like that. And so our definite integral that we're looking at in the reddish thingy, well, we can have dw over negative 2 is x dx, and that's that part. So we have, and now we're doing a substitution where our bounds are changing, right? So we have 0, when we plug in 0 to w, we get 1 minus 0, which is 1, and then when we plug in 1 to w, we get 1 minus 1 squared, which is 0. So our bounds are from 1 to 0 of dw over negative 2 times w to the negative 1/2 power, and then we can do some stuff with that. So let's see, we have that and minus this, right? Yeah, from here and there, and then we can copy everything else down. So we have x arc sine of x from 0 to 1 minus that red part, and scoot down a little bit. So from here, what do we get? We get 1 times arc sine of 1 minus 0 times whatever, okay, minus, and then w to the negative 1/2, that's going to give us w to the 1/2, divided by our new power, which is, okay, so we have w to the 1/2, And then we have this minus that is going to go with that one to go to a plus. Right? And then we have dividing by our powers 1/2. So then what are we left with? That from 0 to 1. Well, can I change it? I can change it from 0 to 1, and then I just make this negative, right? Because if you change the bounds, dx, that equals the negative of your bounds flipped. Right? If we're changing the direction of what our distance is in the horizontal direction, then we just change the sign. Okay. So we just plug stuff in. So we have 1 times arc sine of 1, which is pi halves, so pi over 2, and then minus 0, so that's just 0, and then plus, minus, so minus w, so that's a 1/2, and then I'm going to put a parentheses there, so I do 0 minus 0, right? Okay. So then what are we left with? We're left with, wait, did I mess up algebra? I think I did. Oh yeah, because there's a 2 here. So we have this little 2, so, and so, this is times a 1/2, right? So then 1/2 times something over 1/2 is just 1, so this is a 1. Oh my gosh. 1. Okay, so what are we left with? We're left with pi halves minus 1. Alright, there we go. So, arc sine from 0 to 1 is just, the integral of arc sine from 0 to 1 is just pi over 2 minus 1. Even if we don't see something that looks like a part, it can still be a part, because dx can be dv. So then you're just given that v is x, and then you go on your merry way with integration by parts. You can use substitution, because it's sometimes necessary. It's like a puzzle within a puzzle. And yeah, this whole section is just pretty much doing puzzles. So get your brain on. Let's do it. Alright. How about this? If we have x squared times sine of x dx. Well, if we want our derivatives to go more like away, then we want u to be x squared. So that means du is 2x, dv is sine of x, and v is negative cosine of x. So that means that we get integral of x squared sine of x dx equals uv, so x squared negative cosine x, minus the integral of v, which is negative cosine, so that's a plus, du, which is a 2, and then x dx. Okay. And then I guess we have to do it again, right? Because we have an x and a cosine of x, and that's also sad, so maybe we should just change colors. So we have u is x, so du is dx, dv is cosine, and v is sine. So that means that we have negative x squared cosine x plus 2 times uv, which is x sine x, minus the integral of v du. And what's that? Well, the integral of sine, that's not too bad. That's just cosine, negative cosine, but then we have the negative, so then it changes to plus. So all told, we have x squared cosine x minus 2x sine x plus 2 cosine x plus c. Alright, so you might have to do integration by parts a couple times. Or more times. Alright, so suppose you didn't feel like doing all of that. You could organize your thoughts in a table. This is totally optional and not necessary, but some people like to have tables or charts to help organize their thoughts. It's totally fine. The thing is, though, that you kind of have to, like every time I do this, I have to, like, remember how it works. And so it's kind of like a memorization thing, which some people like, some people don't. But just for the sake of making you fully aware of what's available, here it is. So there's 3 columns in this table. We have pluses and minuses because remember that our general form is integral of u dv equals uv minus the integral of v du. So we have, every time we do integration by parts, we have a sign change, a flip of our sign. So the first column is just changing the signs. The second column is it's not x. Our second column is u's, so what the u values are going to be as we do multiple steps of integration by parts. So that's taking our derivatives. And then our dv's, we are like integrating down. So this we're taking f primes, and then on this column we're taking f integrals. Okay, so to start off we have a plus, and then no, you start with a minus, and then we do a plus, and then we do a minus. Actually, this part doesn't super matter because it depends on how you draw your arrow, but it's fine. So, and then for u, we have, so our first one is going to be x squared, so derivative of that is 2x, and the derivative of that is 2, and then the derivative of that is 0, and after you multiply by 0, there's nothing else to do, so you can stop after 0. And then our other part is sine 4x, so then you integrate going down. So it's negative 1/4 cosine 4x, and then this is going to be negative 1/16 sine of 4x, and then positive 1/64 cosine of 4x. And now you read your table. So looking at this, we're going to have, that's going to be equal to uv, so that's looking this way, uv, which is going to be x squared times negative 1/4. So that's negative x squared over 4 cosine 4x. And then we're going to go like this way. So then we have, we go this way. So we get plus, because negative times negative, is positive x over 8 sine of 4x. And then here we get plus 30 cosine 4x over 32. So 1 over 32 cosine of 4x plus c. And then, I mean, we're going to have 0 times, so then that's going to be, it's like 0 product property, right? So then we get 0 there. So tabular method is an option. It's not necessary. Some people like it. Some people don't. It's fine. All right, here we go. So how do you do u? How do you decide what u is going to be? This is, we're always looking for better acronyms for this, but if you have one, great. One class came up with something about lions and stuff. I don't remember what it was, actually, but lions in something, I don't remember. But it's liate, L-I-A-T-E. So the order of choosing what your u is going to be is first you're going to choose logarithms, and then inverse trig, like arcsine, expressions, and then the algebraic, and that's like x squared or x cubed or something. And then if you don't have any of those, then you choose a trig expression, like a regular trig, not an inverse trig. And then your last choice for u is exponential. Because taking derivatives of e to the x just doesn't go away, and it's really annoying. So exponential is your last choice for u. So let's try this example. We have 6 arctangent of 8 over w dw. Okay, so according to Lee-8, what should we do? For u, we should do the arctan. So we have u is arctangent of 8 over w. So that means that du is 1 over 1 plus 8 over w squared times the derivative of 8 over w because of the chain rule. So that's what, negative 8 over w squared dw. And what's left over? Just move this over. So we have dv is 6 dw. So that means that v is 6w. Okay. So that means that when we have this, we get 6 arctangent of 8 over w dw equals uv, which is 6w arctangent 8 over w minus the integral of v du, which is plus 8 times 6 is 48. W over w squared is just going to give us a w in the denominator, times 1 over 1 plus, what's that, 64 over w squared dw. Okay. And then now we need to do some algebra. So let's see. We get this equals 6w arctan of 8 over w plus, and let's do a brief aside on this. So we have 48 over w times 1 over 1 plus 64 over w squared. So we can just multiply across, so we get, what, 48 over w plus 64 over w, because we distribute. And then, but like, that's kind of annoying, so what can we do here? Well, we could get a common denominator, so we get w squared over 64 over all over w. And then we can, like, flip and multiply, right? So we could do 48 so we get 48 w over w squared plus 64. Barf. Okay. And then how does that help us? Do we need to do a substitution? Heck yeah. So what do we do? Well, if you notice that we have something which we could say is like a u, w squared. I'm going to move this over. So, because our ultimate goal is to, like, integrate, right? So if we say w squared plus 64 is u, and that means that du is 2w dw, that means that our integral of 48w dw over w squared plus 64, we can rewrite with a u substitution of, let me divide by 2. So we got du over 2 equals w dw. But now we have 48 of that, so we have 48 on both sides, so that's 24 du's equals 48 w dw's. And that's what we have here, is we have 24 du over u, and that's going to be 24 times the natural log absolute value of u, so 24 times the natural log plus c, absolute value of w squared plus 64. The absolute values aren't entirely necessary because this is always non-negative, so we get 24 natural log of w squared plus 64 plus c. And that goes over here, so we get, what was it, 24 natural log absolute value w squared plus 64 plus c. Boom. So there's a lot to do there, right? Because we have to do integration by parts, and then we also had to do a substitution. Alright. Cool. Should we leave it there? I feel like we should leave it there. Alright. We're going to start off the next class with a quiz, though. I think that'll be good.